a bit more about this tomorrow. But for this lecture, at least, I really want to make the results seem as intuitive as possible. So rather than starting with some proofs about what kinds of correlations can be achieved in quantum mechanics, I'm going to try to make Bell's theorem seem as intuitively plausible as possible. So I'm going to try to dumb it down to the greatest extent. And so if at the end you think that's trivial, why did he waste my time with that? Because it's so trivial, then I'll have succeeded. I want you to think it's trivial at the end, because it really isn't a mathematically sophisticated result, but conceptually it's extremely significant. So Bell's theorem is important regardless of your interpretational persuasion. But given that for the last few days we've been talking about one particular kind of interpretation, I thought I should segue from what we've been immediately talking about to Bell's theorem. So remember, last time I provided some evidence in favor of hidden variable approaches that take the quantum state to be merely a description of an agent's knowledge. And the nature of the evidence was basically that if you start with a classical theory, you add some restriction on the kinds of probability distributions that can be prepared, you get a lot of quantum mechanics coming out in the sense of reproducing the same predictions that quantum theory reproduces. And of course, in the model that you get, non-orthogonal quantum states were associated with overlapping probability distributions. And so that is why these were psi-epistemic hidden variable models. Now, we saw last time that there was a lot of phenomena, quantum phenomena, that generally people think of as somehow non-classical, surprising, which fell under, which could be explained in these sorts of models. These models aren't purely classical because they add this extra innovation relative to classical theories, namely that there's a restriction on how much an agent can know. So that's a kind of non-classicality that you've introduced into those models. So you could say, well, these sorts of phenomena exhibit a certain kind of non-classicality. You can't understand them unless you posit that agents should be restricted on how much they know, or at least by assuming that, you could certainly explain them within a classical picture of the world. But at the end of last lecture, you might have gotten the impression that, oh, these sorts of models work so nicely. Why can't we interpret all of quantum mechanics this way? Or you might have asked yourself that question. And it turns out that there are certain phenomena that can't be explained in the sorts of models I've described. Okay, and that's over here in the second column. So there's Bell inequality violations, contextuality, quantum computational speedups. Nobody's been able to prove that quantum computers are more powerful than classical computers, but most people in computer science believe that there is a gap between the power of quantum computers and the power of classical computers. So if there is a speedup, then it also won't be explained in these sorts of models. And you can make these lists longer as well. Yes?
We know quantum algorithms are faster than classical ones.
Well, if we think about the kinds of algorithms that lead to a difference of exponential versus polynomial time, so the problem can be solved in polynomial time if, as you scale up the size of the problem, the time it takes you to solve it scales polynomially with that size, and it requires exponential time if the time you take to solve the problem scales exponentially with the size of the problem. So we know, for example, that nobody's ever found a classical algorithm for factoring large numbers into primes on a classical computer. We do have a quantum algorithm for it. So we know it can be done in polynomial time on a quantum computer. If somebody could prove that it can't be done in polynomial time on a classical computer, then we would have the separation. So these kinds of phenomena, you can think of as another kind of non-classicality. If you're thinking about quantum mechanics from this psi-epistemic hidden variable model perspective, you sort of have two tiers. This requires you to assume that there's a restriction on how much we can know. That doesn't do great violence to your picture of the world. This requires some more radical departure from your classical picture of the world. And so that's why, even from this particular perspective, these sorts of phenomena are particularly important. But as I said, that they're also extremely important regardless of your interpretation. So we're going to start today by looking at Bell's theorem, and by the end of the week, we'll talk about contextuality as well. So maybe I should pause. Are there questions about, we sort of sped through the end of last lecture. Are there questions about that sort of approach before I move on? You'll be seeing more of it in tutorial on Thursday. No? OK. Right, so here's my attempt to make Bell's theorem seem extremely simple. First, I want you to consider just a pair of measurements which each have two outcomes. So I'm just going to draw them like this. There's a box. The two outcomes are a green and a red LED light coming on. And it doesn't really matter what these two measurements are, but they're distinct. So I'm just going to label one S and the other T. Okay, so I'm not going to tell you what's going on inside these boxes. All you know is that these are two outcome measurements. And here's the setup of our experiment. A pair of particles are going to be prepared in some way, starting from some source. One particle is going to be sent over here to this location. One particle is going to be sent over here to this location. And in one of the cases, it'll be S that's measured on both. In another case, S will be measured on the left, T will be measured on the right. In another, it's T on the left, S on the right, or both T. And the choice of what measurements are going to be made on the left and the right are each going to be done locally by a fair coin. Okay, so either S or T will be measured here, S or T will be measured there, and there's a 1/4 probability for every pair of measurements. Okay, good. So you have seen this already in Adrian's course, but I'm going to go over it again. And this time there are cash prizes to be won. So the way I want to do it is we're going to play this out. We're going to try to generate certain correlations, mimicking the particles task of generating correlations. And so for that purpose, I'm going to need 2 volunteers to play the role of the particles trying to generate the correlations. Did I mention there are cash prizes to be won for the volunteers?
Cash play.
All right, I'll take Ali. And I'm also going to need helpers. So Catherine, I know you're probably familiar with this. You've seen this before. So you can be one of my helpers if you don't mind. And Sarah, I need you too. OK, so here's your equipment. There. You don't get too attached to this. You get equipment as well. Okay, and your location will be over there. You guys get to stay in the middle because you're like the particles here. Okay, and Catherine, you're the measuring device over on this side. Sarah, you're the measuring device over there. So the random choice of what measurement to make is going to be decided by the coin flip. I've given you the coin. That's the coin that you'll win if you get the correlations right. And so the way it works is that what I want you to do is flip the coin. If it's heads, then write S on the piece of paper. Which wait, not yet, hold on. I'll be doing it later. Sorry. You'll write S on the piece of paper, which means that you're doing the S measurement. And if it's tails, you write T. Okay, and then you guys are going to have, I'm going to tell you what correlations you're trying to generate. You don't know right now. That'll be on the next slide. And then after I tell you what correlations you're generating, you're going to have to decide on a strategy. Then you're going to go off. The coins are going to be flipped. You're going to get the measurement. And you're going to respond by writing on the piece of paper whether it's a red outcome or a green outcome. Okay?
Okay.
So those are the rules of the game. So, and we're going to be watching you to make sure that there's no signs passing back and forth. Right? So you're just going to have to respond only to what you see on the paper. So ahead of time, you don't know what measurement you're going to get. So is everybody clear on the rules of the game? Good?
I'm not fully clear.
Not fully clear.
I haven't
How
seen the
should
next
we
slide.
prepare this thing?
Well, you'll get your challenge on the next slide. But basically, you're going to know what kinds of correlations I want you to generate. And you're going to have to decide, you're going to have a strategy, which is going to be something like this. Okay, if you get the S measurement, then answer green. And if you get the T measurement, then answer green as well. And if I get the S measurement, I'll do that, that kind of thing. Like have a strategy. It could be more sophisticated than that, but that's the idea. Okay, so are you ready?
So can we communicate with each other?
In the beginning, you get to confer, but once you go off and the coins are flipped, then we're watching you. You're not allowed to communicate anymore at that point. All right? Okay, so here is your challenge.
Can we look at it?
Yes, yes. Please. If I didn't want you to look at it, I would have blindfolded you. Okay, so this I've just repeated here. So there's two possible measurements on each side, S and T, with two outcomes each. And they're going to be chosen at random. Okay, so here's the deal. I want you to generate correlations such that if you get the same measurement on the two sides, if the same measurement is made at A and at B, then your outcomes should agree. So if, when I gather the pieces of paper together and I find that the coins came out both heads so that you both got the S measurement, it had better be that your answers were both green or both red. Okay? Then you will win. If they're not, you'll lose. Similarly, if you both got T, then your outcome should agree. But if one of you got S and the other got T, or vice versa, then your outcome should disagree. So take a couple of minutes to think of your strategy. Meanwhile, the rest of you should confer among yourselves about a strategy that would win this game.
Okay, let's leave and discuss.
No, you go ahead, discuss it.
So Andrew always chooses red. And he coughs if he sees pass.
Yes.
And then, red.
I just can't go with the other measure.
They want.
That's why it's cough.
Yeah.
Yeah. I mean, there is no challenge.
No, they're not allowed to call teams. They've actually done them as a call.
No, it is.
But we can do it.
Fine, are they trying to they develop a telepathic bond?
Like you need both of us to go to the and then
They share the
And I clear with
Yeah, I think that's how you do that. Well, it's possible to get one.
It's not even like, no waiting. You can't even talk.
So if you get you're really doing it.
For both of them, or what? But then they always agree.
Right. Like if that's
Okay, so let's do green tables.
so like,
But they have to choose.
I feel like all you have to do is say,
Yeah.
I'm not too.
So then,
Are you ready?
Okay, yeah.
right.
You guys are ready?
I think we are.
So okay,
We are.
you're ready. Okay, so
Oh, it would always be.
we're gonna run this experiment. It's very high tech. And so your role is just
So what if the coin goes on the side?
He gets a coin.
not gonna happen. All right, so go to your stations, and let's have the coins flipped. Okay, take a look at them. Write down the question. If it's heads, it's S. If it's tails, it's T. And now the particles provide their answers. No discussions. No discussions.
Oh, I
So, no communication, did that? Answer. Done? Okay. So now we accumulate the results. Thank you. So what we have is that Sarah is asking S and Kate was asking, sorry, that's right, T, and the answers were red and green, and so you win. Applause. Collective prizes. You each get $1. Thanks very much. Thanks to my assistants. But we're not done. There's more chances to win money. Okay, well, before I move on, let me ask, what was your strategy?
Should we say?
Yes.
That's secret.
No, so
You're not going to get a chance to win money.
if it was S, then it was red. If it was T, then it was green.
Okay. And so it looks something like this. Well, this is the opposite strategy. S green, T red. But what you had to do was get agreement if it's both S or both T, and disagreement if it's S and T. So that's what this diagram represents. And if you answer in that particular way, then you have agreement on the horizontal and disagreement on the diagonal. And so you win. Okay, good. So next challenge is this one. Again, whoever can, I'll give you a chance to think about it, and whoever can explain a winning strategy will win $1. So here, it's similar. The setup is the same, 2 measurements, 2 outcomes. They'll each occur with equal probability. If the same measurement is made on the 2 sides, then the outcomes have to disagree. Okay, so if it's S and S or T and T, the outcomes should disagree. Whereas if it's different measurements on the 2 sides, then the outcomes should agree. So let me give you a minute to think about it, and then I'll take suggestions.
Same thing, but it's the left-handed one.
Are the people distinguishable?
Particles, you mean? Here we're thinking of this as a classical game.
Okay.
So imagine that the particles are classical agents. Yes? Hang on, before you're trying to volunteer an answer as opposed to a question. No more questions about classification, this is clear, right?
No.
I think somebody put up their hand at the back, they beat you to the punch, so I'm going to go for the first. And besides, you've already won $1 of mine, so I'm going to give somebody else a chance. So yeah, go ahead.
So they just have the opposite. So for one, it's T green as red. For the other, it's T red as green.
Yeah, it's that simple.
Yes! Thank you.
This is the best way of getting class participation. Bribery, yeah, exactly. So yeah, this is the scheme. You just do 2 different colors on one side and the opposite on this side, and then you find that across the horizontals you have disagreement, which is the case of the same measurements, and across the diagonals, which is the case of different measurements, you have agreement, and that's what you had. That was the answer. Okay, so final challenge. Here it is. This time, I could only get a toonie this morning and 3 loonies to change for my 5. So this one's worth 2, $2. Here's the setup. When the measurements is T on both sides, okay, T and T, then the outcomes should disagree. But otherwise, in all other cases, so S and S, S and T, or T and S, the outcomes should agree. Okay, so you're welcome to chat amongst yourselves, and if you think you can describe the winning strategy, in a minute, I'll take your suggestions. You really can talk amongst yourselves. Right?
But it's a 1 point, right?
I'm sorry?
don't think you can. The left. You can really do it. That's cool. With this one, the expectation.
Yeah, because then you know
But that's
the certain number.
So
Yeah, but
I feel like you're always going to end up with one.
Oh, one okay, but to get that, you need to have the green green on NTS.
So just always choose green.
One of them always just green. But it's
Or, yeah, either one.
Yeah.
Yes.
You get 3 quarters.
you do better than
So does anyone think they have a winning strategy?
by 3 fourths.
Can this winning strategy involve two entangled qubits?
Or at the top.
Nope.
So
Does anyone think they have a winning strategy that doesn't involve two entangled qubits?
Classical. What about it's not a classical.
what about
No?
No, I mean,
Okay, well, you've already won $1, so
okay.
I'm not going to allow you to volunteer any suggestions for this one. But does somebody else have an idea for if there is no winning strategy, why there's no winning strategy? Nice.
So, the first person has to be able to agree with the second person three out of 4 times, which means the second person always has to choose green, because both S and T or red, I'm making it green, but because both on T and S, he has to have something that the other person can choose. So if you choose green, then you can make the 2 tails green and red. But then you'll have another, the tails with the S, or I guess the heads, the T and the S. But then the first person won't know whether tails should be green or red, so it's going to have to be a coin flip for him.
I'm not sure I followed that
A more physical argument.
precisely. Do you think you could try it another time? Just I guess what I want to hear is kind of a proof that it can't be won deterministically. So, you want to try again? Just a set of claims whose conclusion is can't be done.
Okay, so
Or you could pass the buck.
if you associate, if you associate a color to T and S for the first person, then
The same color, you mean.
well, yeah. So now we'll have to do the same color, because otherwise, there's no way you could agree 3 out of 4 times.
But nothing in the problem says you have to agree 3 out of 4 times.
Oh, but there are 3 different combinations.
I see. So you're saying in order to agree on all 3 of these guys, one of the parties has to choose the same color for both answers.
Right.
Okay.
And then, if that's true, then it means when you have the T and the S, so the first person chooses T and the second person chooses S, that T has to be the same color as the S.
Yep.
But then, because T is the same color as S, T1 is the same color as S2, and S2 is the same color as T2, then T1 is the same color as T2, or you have to guess.
Yes. Yeah. I'm satisfied with that answer. You guys, you tuning. So let me just repeat what you said. Slightly different proof, but saving spirit. So suppose that the person on the right is prepared to answer green for the t. I could have equally chosen red here. It's just with that loss of generality, I can imagine it's green. And then, by virtue of demanding agreement between S and T, this has to be green. And by virtue of demanding agreement here, this has to be green. And by virtue of demanding agreement here, this has to be green. But then I don't have disagreement along here. And so I haven't generated the correlations. And of course, if I had tried to make this red and this green so that I would have disagreement here, well, then I would have not achieved this. And if you really want to, you could go through and put all 2 to the 4 color combinations, and you would always find that one of these links doesn't hold. But it's sufficient to just say that whether this is green or red, you get a sequence of inferences that imply contradiction. So it can't be done. Good. So the probability of winning is at most 75%. Why is that?
Choosing the same color for both.
Sorry?
Choosing a color for both measurements is the same.
So if you chose, say, like in this example, green, you win 3/4 of the time. So what's the proof that you can't do better than that?
Assuming that you're exchanging classical information, you can. The fact that you're exchanging red and green makes it impossible to get the box.
It's just what I just said. Always one of these is going to fail, and you know that the 4 things are done with equal probability. So a quarter of the time, you're not going to generate the right correlations, no matter how you decide to answer these questions. So if we played this game here, you would expect that the contestants could only win, and we played it over and over again, the same rules. You'd expect that at most 75% of the time would the contestants win. So using quantum theory, it can be won about 85% of the time using quantum states. So the question is, just to get a feel for this, how, if we were doing the game here, imagine this happened. We did the game, and the contestants won more than 75% of the time. What would you think was going on? I mean, clearly they must be cheating. How could they be cheating?
Yeah, they could be lucky. I mean, you can't do infinitely many games.
You can't do infinitely many, but suppose that we go on and on and on, and the statistical significance of the deviation, 75%, gets better and better and better. And we're out there at like 1,000 sigma of statistical confidence that this is not a statistical fluctuation, which is the scenario that we have experimentally. Then, what would you say is going on? Hang on, let me give somebody else a chance to answer this one.
They are talking, they are exchanging.
They're talking, they're exchanging, but what information are they exchanging?
The coordinate.
Sorry, the what?
The outcome they one have.
The outcome? Well, they already know each other's outcomes because they've agreed ahead of time on what the outcomes were.
They're exchanging which measurement is being done.
What do you mean by that?
They could tell each other both what measurement is being performed, and then they can agree what results they should have between them. It's like,
That's too much. I mean, it's too much of the information. You can, if they can just blink, if somebody has a tail, then he can blink, and then everything is okay. Because if the other guy has a tail, then he knows what to write down, and
Okay. Yeah. So.
It's the same thing.
So they can try to communicate the choice of measurement that's happening at one wing of the experiment to the particle on the opposite wing. Because if I go back, so say here, the person on the left, there was an agreement that the person on the left would signal to the person on the right if they got the T outcome, right? Then the person on the right can say, depending on whether the person on the left had S or T, because now the person on the right knows whether there was S or T on the left, they can say, well, if it was S on the left, I'm going to answer green for both. But if it was T on the left, then I'm going to answer green here, but red here. And then in that way, you can make sure that you always get the disagreement whenever it's T and T. But if it's S and T, you still get agreement, because your choice of whether to measure green or red here now depends on what's being measured over there. So that's the information that you would communicate to be able to play this game all the time. So that would kind of make sense. If we saw that, we could say, well, clearly they're figuring out how to cheat somehow. But then there's an extra twist, which is, what if we set up the game like this? We move the two contestants to very distant locations, and we set things up so that we demand that the outcome be registered very quickly after the measurement is chosen. Right? So the coin is flipped, and very shortly thereafter, the outcome is registered. So in our game, we would require this sort of rapid turnover, or in an actual measurement in the lab, we would just make sure that the measurement occurs quickly after the measurement is chosen. Whatever this time delay is, I can always just make these things further and further apart, because what I'm trying to do is make sure that this outcome over here is not inside the future light cone of the choice of measurement here. And similarly, the outcome here is not in the future light cone of the choice of measurement here. So this means that that cheating strategy we just described isn't possible anymore, because even if a signal goes out here, trying to inform the other particle of whether S or T was the measurement happening here, it doesn't get to the other end in time, because the particle has already had to choose an outcome. It's already had to commit to an outcome before the signal has even gotten there. So if you set things up like this, well, then you can run an experiment, and you can distinguish between the quantum predictions, the about 85%, and the predictions of a local theory, which says it has to be 75% or less. And what you find is that quantum theory is corroborated. And the question is, how can the particles be pulling off this trick? Good. So the first thing you might wonder, so I'm sort of going to go through just thinking about various ways in which you might be able to get around this result. What if the particles have access to randomness when they're deciding on their strategy? Okay, so you guys could have flipped some coins to decide what you were going to do. And the question is, would that help generate the right correlations? The answer is no, but why?
I mean, you're introducing an extra uncertainty of what your result is going to be for the given measurement. So it doesn't seem possible to, by not being certain what you're going to say in this case, you're no longer certain what your partner has to say.
Right. That you would get less correlation if you had some independent randomness in your choices of answers, whereas the game tells you to generate either perfect correlation or perfect anti-correlation. So any independent noise or independent randomness that is used over here to decide the outcome and over there is information that's not accessible to the other person, and it'll just degrade the correlations. What about randomness at the source, right? So randomness that you agree on. So you flip a coin to decide which of multiple strategies you're going to use. Sure.
Even if you would flip a coin between the best strategy and one that's equal or one that's not as good, it would still only give you choices between the best strategies.
Right. So you have 2 to the 4 different colorings. That each one of those is a strategy. And if I roll some dice to decide a probability distribution over all the strategies, well, every one of them only wins 3/4 of the time. So at best, I'm still only going to do 3/4. If I start mixing in some other strategies that do even worse, that only win half the time, then the overall win probability is just going to go down. So the fact that the deterministic strategies give you at most probability 3/4 means any mixture of deterministic strategies will also only give you a probability of winning at most 3/4. So that was my second question. Let's just skip over it. So now here's another question. If the detector inefficiencies in an experiment are sufficiently high, by which I mean sometimes the particle just isn't detected at all, so it doesn't answer with an outcome. It doesn't answer red or green. It's just silent. No outcome is registered. Then could it be that particles that do obey local causality simulate the correlations on those pairs that are detected? Right? So only a subset of all the pairs of particles that have gone out from the source actually register outcomes. And the question is, could those particles cleverly sort of use the fact that, could it be that when we only see the outcomes some of the time, that on the cases where we've seen the outcomes, we see the game always being won? Is there sort of a loophole here? Hang on, let me give some other people a chance to answer questions, because it seems like it's always the same people who are answering my questions. So let's mix it up.
I guess unless they can contrive to correctly answer the question only when it registers and whatever when it doesn't register. But if it's purely random, I can't see how the overlap would, with any statistical significance, stray in their favor.
True. So if the particles can't influence which cases the detectors don't fire, then it just seems like they'll still get unlucky some of the times. So on a case where they get asked a question which they're going to answer wrong, like say the all green, and they get asked TNT, well, maybe the detectors work on that occasion, and so they're out of luck and they lose the game. But what if if particles actually cause the detectors not to fire? What if the particles carry instruction sets that tell the detector sometimes don't fire?
Yeah, they could only answer when they see S and just answer with green. So then it would only register when it's green, green, and they'd always be right. When it's S, S, and.
So you're saying if they set it up so the detectors only fire when they both get asked S?
Yeah.
So the problem there is though
either detector only fires when it asks S.
I see. So the particles show up at the detector and they take a look at whether it's measuring S or T. If it's measuring T, they say don't fire.
Yeah.
So then in an experiment, I would expect to see that it just never fires when T is the measurement I'm doing. But suppose I go to the lab and I see that the cases of not firing are sometimes S measurements, sometimes T measurements. And for the cases where I do get detections, I see this violation of Bell inequalities. I get a greater than 3/4 chance. What about that case? Yeah.
So one of the particles could always fire regardless whether it's C or S, and the other particle fires only if it's S, but then they switch.
Mm-hmm.
So then you can't know which one is actually going to be the one that has it.
And another thing you could do is you could just run to run. In one run, you could say, okay, in this case, I'll make it the S measurement that doesn't fire, and in the other case, I'll make it the T measurement that doesn't fire. For example, that'd be another way of generate this. So yeah, that's basically the idea. So if I go back to our example here, if it's the case that the left particle is just going to answer green for both, and the right particle is going to look at whether S or T is being measured, and if it's T, is going to cause this to not fire, then on the rest of the correlations, you win, right? So everything's fine. And as long as you sort of change which one's not firing, you won't see that in the lab. And therefore, this is a loophole that in the lab, in sort of the optical implementations of experimental tests of Bell inequalities, actually the detectors cannot be made to fire reliably all the time. And so it's conceivable that the particles do have some local instructions of what to do, and they're the ones who are choosing when the detectors are not firing, and so it's possible that everything is local. So this is called the detector loophole. It's a loophole in the sense that it's an obstacle to asserting with confidence that the quantum world really does violate locality, because it could be using this clever scheme. Okay, what if the choice of measurement is made too early? Is there a problem with getting this conclusion of non-locality?
I'd say that depends on what you mean with too early. I mean, there is a point where the measurement of the other particle may be in the future light cone of the choice of measurement of the too early measurement. This would then be a good definition of being too early. And then,
Right.
of course, there's a problem with that, because then classical communication would in principle be possible.
Exactly. So if the, I think you said measurement, but you meant outcome. So if the outcome over here is in the future light, if this measurement is done so early that the outcome over here is in its future light cone, then of course you could imagine that there's some kind of influence. Even if our current laws of physics don't describe such a causal influence, we could imagine that there exists some influence from the choice of measurement over here to the outcome over there, and so that it could be local. Yes.
Can you also say that, like, some kind of extreme determinism, where the measurements might seem random to us, but they're really fixed by previous states, and then you follow it back and you see that the particles have causal communication with the things that determine which measurement we're doing later.
Yeah.
So then we kind of never have any randomness anywhere, and then everything is local.
Yes. So that's called sometimes the superdeterminism loophole, where if in fact, say I'm using random number generators on both sides, but the physics of what random number decided what measurement is going to be made, well, that can be sort of traced backwards in time. If it's a deterministic theory, then you could say, well, what choice is made is really determined by things further back in time. And if there's a time at which all the information that's relevant to those choices is in the backward light cone of both those outcomes, then you could explain in a local way how you got those correlations. Of course, it would have to be very complicated, because if the way I choose to do the measurement involves, I don't know, just looking at the voltage on some line and, just a bunch of factors that have nothing to do with one another, and, combining them in some strange mathematical way, then the properties in that past, which are relevant to the choice of measurement, are these crazy, they're not simple properties. They're sort of mixed out among all degrees of freedom. And so you need a mechanism for that crazy property to influence the outcomes in the future. So in that sense, it's a bit crazy as an explanation. But it is a conceivable explanation. But what if, so let me tell you about one possible response to that. What if it's the free will of the experimenter that determines what the choice is on either side? So you have two experimenters, and they just choose freely what they're going to measure, rather than letting a random number generator decide. But Jacob, why don't you have a go at it?
So, I mean, in this theory, there would be no such thing as a free choice, right?
Okay, so if you want the superdeterminism way out to salvage locality, you would say you have to give up on free will.
Then the brain is just another complicated random number generator.
Okay. Does anybody else want to comment on that? Go ahead.
Well, so I mean, you could take like the super deterministic, even if everything seems random in the universe, that there's some like greater set of laws that make sure everything's deterministic, and then you don't make any choices. But then from our perspective, where we have free will, we also have a perspective of non-locality. So we'd still be confronted with that kind of problem. It's just, I don't know, it just kind of seems like even if it might be a pleasing way of thinking about something, it might not resolve any issues for us in terms of everyday practice.
Yeah, the question in the superdeterminism is probably if there's any way to have access to the information about the superdeterminism. And usually you don't. And so that model won't help you. I think. Because there's no way to check this. I mean, the information or the state which determines the later measurements, we won't be able to access this state and to say, okay, I'm not free of. Also, I mean, I can still feel free, and you can say there is a free will, but the point is that whatever I do is determined by something in the past, and if I have access to that state in the past, I can determine all later measurement outcomes. But because I don't have, or I won't have access to that state, I think it's, as Lance said, for practical or for everything we can describe in nature, we can't distinguish between superdeterminism and.
So, if I understand you correctly, you're saying I would still have the illusion of free will as long as nobody were able to, say, predict my actions. And because nobody is able to sort of do that, it's okay that in a deterministic universe I can still have the illusion of free will. Is that right?
That is on free will, but also on the measurement, namely locality. The theory of superdeterminism might or will have locality as a property, but for practical use, there's no way to check if superdeterminism is true. So it's
I see.
I can't see the use or why it is useful to use that theory. Maybe just to feel good, but
well, it's a bit like the Plato's cave. That had it been that the only kinds of correlations we saw would satisfy these Bell inequalities, then we might still have been in a scenario where we have limited information about the hidden variables, and therefore we can never predict what the outcomes are. But nonetheless, we could be confident that there could be some local explanation of those, even though we ourselves cannot predict it. But what Bell's theorem shows is that barring this superdeterministic explanation, there cannot be any hidden variables that can locally explain our correlations. And so one thing that's interesting, which sort of ties into what you're saying, is that you can prove an interesting result if you assume that you're in a world where the Bell inequalities are violated, but also there's no signaling fast and speed of light. And that result is that there must be some unpredictability. So there must be some things you don't know. And that seems to me to be the same sort of flavor as what you're saying, that you're going to be limited in your predictability. Is that right?
Mm-hmm. But, okay, you can really prove that.
Yeah, you can, let me see if I remember. Yeah, that's right. You cannot predict with certainty the outcomes of experiments in a world that was no signaling and violated Bell inequalities. Maybe I'll try to include that in tomorrow's lecture. So other comments about this is called the locality loophole, by the way. So that if you do an experiment and you haven't carefully ensured that the choices of measurement are made outside the future light cones of each outcome, then you haven't sealed the locality loophole. The experimental situation right now is kind of interesting. So there are experiments that seal the detector loophole, but don't seal the locality loophole. And there are other experiments that seal the locality loophole, but don't seal the detector loophole. And currently, there's no experiment that seals them both. that's probably something we'll see in the next few years. An experiment that really rules out both those guys. Okay, so what's the mystery of Bell's theorem? If you want a realist explanation, so we're not being operationalists here, we're asking for a realist explanation, then there's a tension. Because on the one hand, there's no superluminal signaling in quantum mechanics. I'll say a bit about that in a moment. So you have no dependence of the experimental statistics at one wing on the choice of measurement at the other. And yet you do have a dependence of the particular outcomes you get at one wing on the choice of measurement at the other. As we saw in the Bell example, that one of these particles is going to need to know what the outcome was on the other side to be able to explain in a causal sort of way how you get correlations. So I'm not saying this is the way you should necessarily think about it, but one way of thinking about Bell's theorem is that there's this tension. Why should it be that we have superluminal causal influences to explain these correlations, and yet we can't use those influences to send signals? That seems odd. Was there a hand up somewhere? No. Okay. So I want to end with telling you a bit more about the situation in quantum mechanics, because nothing I've said so far has involved quantum mechanics at all. I've just said that the Bell inequalities are something you can derive for any theory which is local. Okay, so where your causal influences propagate less than the speed of light, you can say that your correlations have to satisfy certain inequalities. So that's a statement about a set of theories. It's not a statement about quantum mechanics. What you can say about quantum mechanics is that it's not one of those theories. It's not a local theory. It violates the inequality. So here's just a more formal way of saying what we've been talking about. So if I express the probability of getting agreement between the outcomes of two S measurements this way, is the probability of agreement for S and T, T and S, and this is the probability of disagreement for T and T, and I weight those with probability a quarter each, that's the probability of winning the game. And what we saw was that if you're limited to these local strategies, then your probability of winning the game has to be bounded above by 3/4. That's an example of a Bell inequality. But quantum theory predicts about 0.85, and so it violates that Bell inequality. So how does quantum theory do that? So far I've just told you it does. Probably you've seen this in Adrian's course, so let me go over it quickly. Here's a pair of choices of measurements that will do it. So over here on the left, well, first of all, I should say the two systems now are qubits, two-dimensional quantum systems, and the measurement over here on the left, corresponding to T, is the Z-spin measurement, corresponding to S is the X-spin measurement, and I'll just assume conventionally that green will be the up outcome and red will be the down outcome. And then over here, you're doing, for S, you're doing a measurement along Z plus X, and for T, it's X minus Z. And again, the up outcome is going to be green in both cases. So those are my choices of measurements. I prepare the two qubits in this entangled state. And I'm trying to, what I'm going to show is that you can get these kinds of correlations with this probability. And here's how it works. So this should be familiar to you by now. If I say I measured along some spin axis n on system A, what do I collapse system B to? So system B starts in this entangled state here. Let me write my spin state as just cos theta over 2, 0 plus sine theta over 2, 1. Right? So that's some angle in this plane. And then it's steering. So you've seen this twice already in this course. You collapse the distance guy to just the same superposition of 0 and 1. So you collapse B to plus n. If you measure plus n on the left, you collapse B to plus n on the right for n's in this plane. And so now I know I can calculate easily what's the probability of getting plus n here and plus m over there. I just take the overlap of plus n tensor plus m with psi mod squared. But I know that this guy acts on psi and leaves me with an n state on B. So it's just the overlap of m and n on B mod squared. And that's just cos squared theta over 2, where theta now is the angle between m and n. So I guess in this example, that would m here would be the z axis. And so now if I look at the angle, for instance, between getting the S up outcome over here and the S up outcome over here. That's just this angle here on block sphere. So pi by 8. So I plug pi by 8 into that formula, and I get 1/2 plus 1/2 root 2. Sorry, I think I said that wrong. It's a pi by 4 separation between state I collapse to, S green, the state here, and S green over here, and plug that in, I get pi by 8, 1/2 root 2, and that's about 0.85. And then you can just sort of go through and say, right, the cases where I'm supposed to get agreement, like I'm supposed to get agreement for S and S, the separation between the state I collapse to here and the outcome I'm supposed to get is pi by 4. If I do S and T, then I collapse to S here. The separation to T green is pi by 4. If I do a T measurement here and an S measurement there, and I get the green outcome, then I collapse this guy here. Again, it's pi by 4 separation. But if I do T on both, right, so I do T here, I get the green outcome, I collapse to this guy, now I have an 85% probability of getting the red outcome, because the red outcome is close to the state I've collapsed to, and the green outcome is far from the state I've collapsed to. So T and T is the one case where you're going to get this anti-correlation. So you get this 85% probability for all 4 cases, and that's why you violate the Bell inequality. So the final thing to see is why there's no signaling in quantum theory. So imagine you do something even more general, right? So rather than the particular entangled state I described in the last case, take some arbitrary state on A and B, and take some arbitrary POVM on the left and some arbitrary POVM on the right. Label these outcomes by K and those outcomes by J. And now we want to know, do the statistics on the right depend on the choice of measurement on the left? So I want to know about P of J, the probability distribution over J. And so to do that, I should just calculate the probability of joint outcomes, K and J, and then sum over K. So I just take the marginal for this. The probability of the joint outcome K and J is just going to be the trace over A and B of rho AB times EKA FJB, right? So this is the operator I use for the kth outcome here. This is for the jth outcome. This is the way I should calculate that probability. And now here's the point, that if I have a sum over K out front, I can move that into the trace, sum these guys, and because they're POVM, they're identity. And it doesn't matter which POVM I'm measuring, they always sum to identity. So the expression for P of J depends only on the choice of measurement on B, and does not depend at all on the choice of measurement for A. Okay? And therefore, if you go and you look at the statistics you see, you cannot infer, for example, whether a Z or an X spin measurement was made here. There's no information about that. And ultimately, the reason for this is that we've assumed that the measurement on A and the measurement on B are represented by POVMs of this sort. The measurement on A is just identity on B, and the measurement on B is identity on A. They commute. So there's actually an assumption in quantum theory that guarantees the no signaling, which is that when you do measurements at space-like separated regions, the operators you associate with those measurement outcomes are commuting operators.
Wouldn't this commute anyway, regardless? Because I don't think you need to assume anything about how it's just the fact that if you have A times identity and identity times something else, they'll commute anyway, because when you multiply them, all they see is like, I mean, if you just multiply this first one, E times identity, and identity times F, and you multiply those together, that's just E times F.
Yes.
And the same thing when you do it the other way.
Yeah.
So I think it commutes regardless of any additional.
Yeah, I agree. Once you've assumed that this is the way to represent measurements on A and B, then commutation just follows as a mathematical consequence. I guess what I'm saying is, equivalently, you could say the measurements commute, or you could say the measurements are modeled by this sort of tensor product, one on one tensor factor, one on the other tensor factor. Either way of expressing that assumption, it is the way in quantum theory that you model measurements that are done at space-like separation. And it's what guarantees that there's no superluminal signaling in the theory. So to some extent, you've built no superluminal signaling into the formalism by choosing to model measurements in these ways. So that's the tension between the fact that there isn't any signals and the fact that to explain the strength of these correlations, it seems one needs to appeal to superluminal causal influences So let me just skip this and actually maybe I'll just ask if there are any more questions, and next time we'll come back to this stuff. So the punchline is that there seems to be a tension in quantum theory. This is why Bell's theorem is so important. So on the one hand, you have no superluminal signaling, which is one of the central principles in the special theory of relativity. And on the other hand, you have Bell correlations, which seem to require superluminal influences if you want to explain those correlations causally. Now, some people might say, well, why do we want to explain correlations causally? But that's sort of what we do in science. Like if I'm a doctor and I say, oh, there's a correlation between smoking and lung cancer, then somebody might say, well, does smoking cause lung cancer? That's what we really want to know. If they responded, well, I don't care about causes, it's just correlated, that's all there is to say, you'd say, well, no, that's not enough. We want a causal explanation. So you might want a causal explanation here as well. And therefore, in the end, you have this strange tension between the theory of relativity and quantum theory, which are really the two pillars on which modern physics is built. And that's why people in foundations have spent a lot of time worrying about this problem. And I would argue that we still today don't have a good answer to the question of how should we resolve this tension. Certainly there's no agreement in the community about how should we think about this. Partly because there's no agreement about how to interpret quantum mechanics. But to my mind, nobody has really provided a satisfactory answer to relieve this tension. All right, let's end there and come back to it next time.